In these examples, we're going to determine some answers without using a calculator. We're going to use our approximation skills. We'll try to do this to within 10% accuracy. So in the first one, adding up and subtracting these numbers, notice what I see here is a bunch of relatively large numbers. As I scan through, I see that it's 97, 104, 300 and some, and then subtracting off something small. My sense is that we can approximate this as 100 plus 100 plus 300 minus something that is small compared to all those values, so approximately 0. I would approximate this as 500. If you actually put this in your calculator, you'll find that at least to 3 sig figs, the answer is 506. But if you compare 506 to our approximate answer of 500, you'll see that that is only a 1% error, which is pretty good if you're trying to make an approximation. In the second one, we've got a large number times a large number divided by a large number, and then we're going to add 3. It's not yet clear that we should drop that 3. So instead, let's be a little bit more careful. 101 is close to 100. That gets multiplied by 98, which is close to 100. And that gets divided by 249, which is close to 250. To that, we're going to add 3. And again, let's keep that around for a little while. This could be written as 10 to the 2 times 10 to the 2 and divided by 2.5 times 10 to the 2. Now, there's not necessarily a right way to do this, but I'll show you the way that I like to think about this. I'm going to write this as 10 to the 1 times 10 to the 3. You can manipulate this however you want, just to make sure that you've got 10,000 on the top. And what I'll do is I'll divide the 10 to the 1 by 2.5 and divide this by 10 to the 2. The rules about multiplication inside of fractions allow you to do this. The 10.1, the 10 to the 1, that's 10 divided by 2.5, that's 4. Okay? 10 divided by 2.5 is 4. On the top, we've got 10 to the 3 divided by 10 to the 2, that's 10 to the 1. And what I've forgot to do here is include this plus 3. You can see that this is approximately going to be 40 plus 3, or 43. If you then actually check, what would you get with your calculator? You would get 42.8, at least to 3 sig figs. Notice that that is a pretty small error. It's about 0.5%. So pretty good. Part C, pi squared over 6. If you're real quick and sloppy about this, you might approximate pi as 3 and let that get squared and divided by 6. And that would be 9 over 6. Or 1.5. However, when you're doing squares of things, you need to be a little bit more careful because the errors that you introduce in approximation tend to get enhanced. If you instead remember that pi is close to 3.1, this is like 3.1 squared over 6, then that 3.1 squared is closer to 10 than it is to 9. So I might better think of this as 10 over 6. If you do that, this is the same as 5 over 3, or 1.6 repeating. So let's round that to 1.7. Now let's check the actual answer that you would compute here. The actual answer is 1.64 to 3 sig figs. But notice that the difference between 1.64 and 1.7 is pretty small. That's about a 3% error. So quite good. The remaining two we have to do is 3 times root 37. The idea here is to notice that 37 is close to a square root that you probably know. This is approximately 3 times the square root of 36. We've made a lower estimate here, and so we should expect that the real answer is going to be a little bit bigger than what we find here. 3 times the square root of 36 is like 3 times 6, or it is equal to 3 times 6, so we might estimate this answer to be 18. The actual answer is 18.2, a little bit bigger. But notice that that is also about a 1% error. Finally, E involves the cube root of a number. One way to think about these problems is to figure out what happens when you take the cube of certain numbers. So before we even begin, let's make a little list of 2 cubed is 8. 3 cubed is 9 times 3, which is 27. 4 cubed is 16 times 4, which is 64. 5 cubed is 25 times 5, which is 125. Notice that 130 is not far from 125. It may not be a bad idea to approximate this answer as 125 to the power of 1/3, which you should see is equal to 5. So if we make our estimate equal to 5, then we can compare that to the actual answer. The actual answer is 5.07, which is quite good, and an error of about 1%. Notice that here, when you're taking roots, square roots and cube roots, when you make estimates, it tends to reduce the effect of that error.